Okay, hi everybody. Welcome to the first FORCE seminar of fall 2024. Thanks for joining us today. I'm Kara Brugman. I'm a research scientist and the outreach coordinator for FORCE.
And I'm Kyusetsuno, research scientist of the FORCE.
Before we get into the seminar today, I did want to remind you that you can see videos of our previous seminars up on YouTube. This video will be posted next week, and if you're on our listserv, you'll get a notification of that. We have 3 more seminars this semester in October, November, and December, given on a wide variety of topics, including our seminar on December, which is about the IHPV. So if you're curious about the IHPV, don't know much about it, this is your chance to learn about it. And I want to remind everybody that our 3rd winter workshop will happen in January. It will be online only, and there'll be information about how to register for that in the coming month or so. You can mark your calendars. Okay, without further ado, our first seminar of the semester about Twister, our torsion press, from Jorge Cubero Sesín.
Okay, so we are pleased to invite Professor Jorge Cubero Sesín as a speaker for the 4th seminar. And Jorge specializes in nanostructured metallic alloys, synthesizing them through high-pressure torsion and examining the microstructure with application to the biomedical and the energy field. So he obtained the PhD in Department of Materials Science and Engineering, Kyushu University in Japan, under the supervision of Professor Zenji Horita. And now he's an associate professor at the Costa Rica Institute of Technology. So today he will present his ongoing research on metallic alloys. So Jorge, you can start. Yeah.
My name is Jorge Cubero. I come from Costa Rica Institute of Technology, Instituto Tecnológico de Costa Rica. And today I'm gonna talk to you about our research work. And I'm gonna share mostly what we've been doing for the past 10 years and mostly the more recent years in nanostructured metal alloys. And I'm gonna focus in biomedical applications, especially biomedical alloys, and also a little bit of battery research, battery anodes, and some other topics if time allows it. I'm an associate professor in the School of Materials Science and Engineering, and also I am in charge of our research center for materials and research and extension. And we have been doing work with some collaborators throughout the years, which I would like to acknowledge at this point. In the University of Costa Rica, the Electrochemistry Center, also the National Nanotechnology Lab in San Jose, Costa Rica, also some institutes and universities in Japan, including Kyushu University, Eisner, Kumamoto University, and the Magnesium Research Center, and also the University of Quebec at Trois-Rivières from Quebec, Canada, and the Hydrogen Research Institute over there. So just to briefly introduce our place, our research center. Our university is located in the center of Costa Rica. It's a city at the east of the Central Valley, about 50 kilometers from the city of San Jose, our capital city. It's a public university founded in 1971 in the city of Cartago, and the main campus is located there. And we have a few other campuses all over the country. And the main campus, we have 13,000 students approximately, including graduate and undergraduate students. In the School of Materials Science and Engineering, we have a research center called CMTech, Center for Materials Research and Extension, and we have some capabilities. It started in the 80s as a metallurgical department, and has evolved over the years into further material science, but we still keep a strong metallurgical base, and we have some equipment capabilities to carry out research and also services to the industry, local industry in Costa Rica. And in general, the medical device industry has been developing significantly in Costa Rica, so that's driven a lot of our research to the biomedical alloy topics, but also it's growing in some other fields. Semiconductors is one that is hot right now, but some others as well. So you can see there a list of our main capabilities that most of the results that I'm going to show you today are done or obtained in our research center. So here is just a few images to show you, and because of this audience, of course, is interested in the twister and the high pressure torsion, as we call it, the machine. We started this lab about 6 years ago, and gradually have been able to get some equipment. We initially started with a very small scale 10-ton HPT machine donated from Kyushu University in Japan. And then we were able to upscale our HPT facility to the machine you see number 3 over here. I think I can use a pointer probably. So the machine over here, this is the time that we installed the hydraulic press. It's a 200-ton hydraulic press. And in this 200-ton hydraulic press, we designed and installed a torsion system. And the torsion system was developed here locally. And it has a little bit over 6,500 Newton meters of torque. So it's a very robust torsion system. So it's capable of sustaining the load and then applying the rotation, as you probably know, and I'm going to explain a little bit later. We can make tool steel dies here in Costa Rica locally, and also we can get tungsten carbide and cobalt alloy dies for higher hardness materials. And we can process 3, 10, and 20 millimeter diameter HPT samples. As you can see here, this is our 20 millimeter die. We also have the capability to do ECAP, and we have just one ECAP die. It's either 90 degree or 120 degree 10 millimeter diameter bars that we can press using roughly the same press, and just exchanging the HPT die and using the ECAP die without applying any rotation. So this is our main processing capabilities, and mostly our 200-ton HPT machine is the most busy. So just as a brief introduction, I would like to talk about why do we do high pressure research, especially high pressure torsion in metallurgy, and apply it to a wide variety of metal alloys. So traditionally, when we talk about traditional conforming methods like cold rolling, as you see on the left, the deformation is carried out at ambient pressure. So that's when we introduce a lot of strain, defects and dislocations accumulate, and grains orient themselves according to the slip, most favorable slip along the deformation direction, and that will cause grain refinement. And grain refinement is of course accompanied by the reduction in the macroscopic shape of the workpiece. But also the accumulation of dislocations and defects will increase the amount of strain, and then this will eventually lead to sample failure if we do excessive plastic deformation. But if we increase the pressure, so if we increase the pressure to in the hydrostatic way with large plastic strain, then we can apply much more deformation to samples. So the most research, probably most famous SPD, severe plastic deformation process, is a high pressure torsion, as you can see on the image on the right. And traditionally, we put a sample, disc sample, between 2 ambials, and these ambials are the ones that I mentioned before. It can be tool steel or can be a harder material if we want to process ceramics or oxides or some other hard materials, intermetallics, or high entropy alloys, and the sort of materials that can be processed. And then we can apply high pressure and deformation by rotation of the lower ambial. So the rotation of the lower ambial will produce significant creation of dislocations and deformation, but the hydrostatic pressure will usually keep crack propagation at rest. So the material can accumulate a lot more of crystalline defects, and these crystalline defects will evolve into usually bulk ultrafine-grained or nanocrystalline microstructures, as you see on the right. So before the processing, we usually have coarse-grained microstructures in metallic materials, and then usually after SPD processes like high pressure torsion, we will get to break down these grains into much smaller grain distributions. with the ultrafine or nanocrystalline size usually well below 1 micron, and that will change depending on the metal alloy that we process or the crystalline material that we process. So it is also considered a top-down nanotechnology synthesis technique. So just to go a little bit deeper into what has been proposed and research throughout the earlier years of severe plastic deformation is as I said, when we use hydrostatic pressure, most of the deformation goes to the material, the strain goes to the material, and especially to shearing and creating a lot of crystalline defects and not change the overall shape of the workpiece. So in SPD, one of the criteria is that we should not significantly change the shape of the workpiece. And by doing this, we can increase the pressure and then be able to introduce a lot of crystalline defects. And these crystalline defects will evolve with the amount of deformation, first into high density clusters, and these clusters will eventually form into subgrain boundaries, and these subgrain boundaries will probably recrystallize into smaller grains. And then most metal alloys will reach saturation grain size. And this saturation grain size occurs because of a balance between dislocation generation and dynamic recrystallization of the grain. So in a wide variety of ductile metals, the grain size can be significantly reduced when you compare it to conventional methods of plastic deformation. And also we can do it to very hard materials and get usually even smaller equilibrium grain sizes. So it's possible to tailor the fraction of dislocation or the dislocation density of these materials and also the grain size. And we can also, of course, use heat treatment to further tailor these microstructures. So it has been a very classical approach for the SPD research for, I think, already more than 30 years to try to tailor the structural properties, mechanical strength and ductility for many metal alloys. So as I said before, we have many traditional and also newly proposed SPD methods, such as the high pressure torsion or the equal channel angular pressing, but many new processes have been developed to try to upscale the work pieces that we can make from these processes, because usually when we constrain the material is that when we can get the smaller grains, and it's of course takes very large machines and very large loads to upscale the size of metallic work pieces. So many new continuous or methods that are in tandem and also increasing usually the form factor of the workpiece have been developed and are currently still being researched to upscale the size of the workpieces. But in general, the objective, as I said, is to produce bulk ultrafine grain distributions. And one of the positive aspects is that we can get very high density, no porosity, with a relatively easy way to do it. We don't need to use any special atmosphere or vacuum or increased temperatures. So usually the cost is just driven by the energy input to the hydraulic press and the torsion system. And it can be done in a wide variety of materials, as I will show you later. We can mix very effectively, even metals with very different melting points or low diffusivity. And that's also a very interesting aspect of the matter, because we can, for example, consolidate metal alloys or other crystalline materials from the elemental powders. And we can achieve a very nice distribution of powders and second phase particles, for example. And as I will mention also a little bit later, phase transformations under the high pressure that are stable even after we remove the pressure. So these are more or less the background of the field of high pressure torsion. As I said, we can produce any sample that's circular in shape, like a disc or a ring, and cylinders will also be able to do it, but we have to control the height to radius ratio, the height to diameter ratio in order to get a very homogeneous or a more homogeneous grain distribution. But it's also possible to upscale in the thickness of the sample. And usually the strain in high pressure torsion is associated with the shear strain in torsion. So usually N would be the number of turns, R would be the radius from the center, and H would be the sample thickness or the sample height. And then, although there's been some controversy around it, people argue about the what continuous or von Mises or some other continuous deformation criteria we should apply. But for example, logarithmic strain or von Mises strain can be used to calculate the equivalent strain that we can apply with the HPT method, and so that we can compare it with other SPT methods such as ECAP and others. As I said, powder consolidation is possible. For example, here we are looking at titanium oxide powders, and even hard ceramic materials like titanium oxide can be sintered with very high relative density, or very close to 100%, and a very good control of impurities, because the limitation is only the oxide. For example, if these were metal particles, then the oxides, only the surface oxide in each particle will be introduced. But since we don't increase the temperature, we don't induce oxidation from the atmosphere. We don't need to control the atmosphere. And because the sample is constrained, in general, most of the air will be driven out by itself by the pressure. So it's a very nice way to synthesize, especially in the academic field, specialty alloys or ceramics or oxides or some other interesting materials that also have been studied in very recent years, like photocatalysts or high entropy alloys. And as I said also before, people have tried to increase the sample size and also to do these processes in a continuous way. So for example, in the image is the continuous high pressure torsion method, but there are some others also in the literature, as well as the ECAP process that has been used or worked a little bit more in terms of large sample or continuous sample production. And it's a very important ongoing challenge in SPD research, that is to increase the sample size and the time that it takes to process a ultrafine-grained material. So it's more or less what's been going on. In terms of the very recent years, as I said, in the very classical start of the field, that most of the research was carried out to improve strength and ductility, and investigate the relationship between grain boundaries and grain defects, boundary nature with the mechanical properties, of course. And that led to very important, formulations of the defects of the SPD process material, the grain boundaries. And it's not only that the grains are small, but that the average width of the grain boundary is thicker, that the grain or the defect concentration in the boundaries is higher than in conventional materials. So there's a lot of free volume, or there's more free volume within grain boundaries. And that also increases, for example, diffusion activity, and changes the nature not only of mechanical properties, but also some other functional properties that are driven by grain boundaries. So since we reduce the grain size, then the finer grains have more atomic mobility, diffusion is accelerated, and because of the surface volume of grain boundaries is higher than in comparison with coarse grain metals. So it has started a lot of research, for example, in biocompatible metals, where we need to improve, for example, tissue integration, also degradability, as we will see, corrosion resistance, not only in bodily fluids, but also in general with any corrosive or chemically corrosive media. Also because of the high mobility, then it has been thoroughly researched for hydrogen storage in many types of materials, and now it's going a lot into the intermetallics, high entropy alloys, and some other materials, also radiation resistant materials, photocatalytic oxides, and also nitrides. And a little bit also traditionally was the superplastic forming that is important for metal alloys as well. So I'm going to talk a little bit of our two research results in several metal alloys that are from the biomedical field first. So the first topic I'm going to talk about in general are titanium alloys, and then we're going to go looking at some of these titanium alloys. So in general, for permanent implant applications like hip prosthesis or knee prosthesis or spinal fixation devices or dental implants, titanium alloys are the most used alloys today, especially replacing stainless steel and also cobalt chromium, for example, because of their improved mechanical compatibility to the human bone. So in general, the elastic modulus, the Young's modulus of titanium alloys is somewhere ranging between 80 and 120 gigapascals, which is an important improvement from, for example, steels that are around 200 gigapascals in terms of the mechanical compatibility with the human bone, especially for this kind of bone implants. So also, of course, the tissue integration and the sterility of the titanium surfaces in the human body are much improved. And also with a good mechanical resistance, especially achieved by alloying titanium with some other elements, are driving the research of titanium alloys, not only the commercial purity titanium, but also the beta phase titanium alloys. So traditionally, the pure titanium will crystallize in the HCP alpha phase, which has some mechanical properties, and especially the elastic modulus of the alpha phase is around 100, 110 gigapascals. And it's usually the microstructure where commercial titanium alloys like CP titanium grade 1, 2, 3, and 4, or for example, titanium 6 aluminum 4 vanadium, which is grade 5, one of the mostly used, or 6 aluminum 7 niobium, which is a grade 32, which are an alpha plus beta type. So once you introduce several beta stabilizing elements, then we will get transition to the beta phase, which is a BCC structure. And what's interesting about the BCC beta phase is that the elastic modulus will usually decrease, usually from 60 to 80 gigapascals, using usually alloying elements such as molybdenum, vanadium, or niobium. Then we can increase the fraction of beta phase. If we increase further this amount of beta stabilizing elements, then we can get a fully beta type, for example, titanium alloy. But the strength of the beta type titanium alloy has to be tailored carefully, associated with the processing, material processing. So it's not so easy to get good mechanical properties from beta type titanium alloys, and has been researched as well. And also we can get some sort of near beta type, which is a mixture of alpha plus beta, or close to beta. And this is what's traditionally been done for titanium alloys. In general, commercial purity titanium, as we will start with this material, has some interesting factor that it also has allotropy in terms of the change of pressure. So commercial purity titanium will change to a omega phase. It's a simple hexagonal crystal phase, which is different from the hexagonal compact phase, alpha phase. And this is a reversible transformation at pressures from 2 to 6 gigapascals. And what was discovered by processing commercial purity titanium by HPT is that we can produce a high fraction of the omega phase, and then this omega phase will stay after we remove the pressure, will be stabilized by the small grain size and the defects that are generated by the HPT process. So usually the omega phase transformation can happen by pressure. The reverse transformation in very pure titanium can be reversed by removal of the pressure. but also it can be removed by increasing the temperature somewhere between 100 and 200 degrees C. So if we apply high pressure torsion to commercial purity titanium, we can find that we can get the omega phase stable in a high fraction. And the omega phase usually has a higher hardness, and it may be used in some interesting applications, especially because we can then increase the strength of commercial purity titanium without the need to add alloying elements. So we have been working with commercial purity titanium for some time now, and I'm going to show you some results. So very traditionally, what we do, and this is probably going to repeat itself for other alloy systems that I will show, is that we can take, after we process by HPT, we can grind and etch and polish and etch the sample to reveal the microstructure by optical or electron microscopy. We can take hardness indentations, and as I said before, the strain will depend on the radius of the sample, also the number of turns. So measuring a few radii from the center to the edge will give us a nice distribution of how the microstructure is evolving. And microstructural evolution I will talk about a little bit later, but as I said, once we get a steady state grain size, a saturation grain size, when dislocation generation is balanced by dynamic recrystallization, we will not get further refinement with HPT processing. So this gives a chance to material that's closer to the center to evolve into the fine grain size that we can get firstly in the periphery. So depending on the number of turns, depending on the distance from the center, we can get, or we can control as much as we can, the homogeneity of the ultrafine grain distribution in this way. So measuring the hardness is important for this aspect. We can also remove by EDM, by electrical discharge machining, for example, small size dog bone specimens for tensile testing. And then, of course, we can carry out microstructural observations by TEM, EPSD, or others. So just very briefly, looking here, we did some interesting work changing the pressure as in the commercial purity titanium. Especially, we knew that the changing the pressure, for example, from 2 to 6 will change the fraction of the omega phase. But if we really want to narrow down and tailor how the omega phase, how much of the omega phase is formed and how is it formed, we wanted to change very systematically the pressure and as fine as we could. So in general, when we increase the pressure, then, for example, in the case of this study, we didn't see the omega phase with 2 gigapascals, but when we increased, for example, to 5, and we did this like 3, 4, 5, and 6, and then we went somewhere between 5 and 6, 5.2, 5.4, and the sort of analysis, we discovered the change in the fraction. And you can see the peak of the omega phase here increasing at the expense of the alpha phase. And also we tried aging and then aging and seeing how the aging will change the stability of the omega phase. So actually, this is kind of an ongoing work, and we've seen that the thermal resistance of the omega phase it's better when we do a fine grain, or we produce fine grains by HPT. This is, for example, 130 degrees C for 20 minutes, and we still see the omega phase. And this is something that we've been testing and we're doing at the moment. So here is actually plotted the hardness of this kind of material against the distance from the center. And then you can see the effect of pressure on the hardness and the distance from the center. So 2 gigapascals, 4, and 5, 5.25, 5.5, and 6, as you can see here. Then we will get an increasing hardness a little bit gradually at the beginning, but once we get to a higher pressure, then there is a little bit more significant step up in the hardness. Just as a schematic here, this is the area of the disc where we usually take our tensile test. So we can compare the hardness that we get here with the actual testing of the tensile strength here. And then if we age it, actually, something interesting happens. So as I said before, the microstructure is evolved firstly at the periphery. So usually this is the area with more defects, dislocations, and when we heat treat it, then usually this is the area that recrystallizes, statically recrystallizes first. So we get static recrystallization, and at this point of the aging, that's 20 minutes for 130 degrees C, then we see that there is a, there is this material still thermally stable, but the hardness is dropping. So probably if we increase the aging time or the aging temperature, we will see the drop of the rest of the material back to the normal or closer to the initial state. And of course, this is also related to the reverse transformation of the alpha of the omega to the alpha phase. But one of the most interesting results here is where we lose the ductility, which is the other important aspect of the equation, where we lose the ductility. And we see that if we go find somewhere between 5.25 and 5.5 gigapascals, we lose the ductility a little bit abruptly. So this is something very interesting, and it's actually something that we are very interested into further investigating with deeper microstructural analysis that the ones that we are capable to do here in Costa Rica. So something interesting to see that somewhere between 5.25 and 5.5, then we see the loss of ductility. The hardness or the strength keeps increasing. It seems also getting to a saturation here somewhere around 1,000 megapascals, which is actually great hardness, great strength for titanium alloy, but ductility. So we can tailor, as I said, and we are investigating how about which heat treat this condition or this condition, what kind of properties we can get. If we look at fracture surfaces, it's interesting where we see that at some point the fraction of omega phase makes the failure mode change from ductile to brittle, and that's something that, as I said, we're looking into investigating a little bit deeper. How much of the omega phase or what characteristics do the omega phase has when it's increasing the pressure and the strain, as I showed before. So we did some hardness measurements of the tensile samples, and we see something interesting that actually at the tip of the samples, for example, are 5.25, we see a decrease in hardness after we pull. So we also think that probably the loss of ductility is associated with a dynamic change in the fraction of the omega phase, reverse transformation at some point, driven by the tensile strain, and this is something that we're looking into. We actually, what we did is we took fine hardness indentations along the tip of the tensile specimen, the failed tensile specimen, and comparing samples at the 5.25, and 5.5 gigapascals, and we see, there's a hardness drop, especially in the 5.5 and 5.25, and that doesn't happen when we do 5.5. So something related to the stability of the omega phase probably is also a factor, so that it doesn't go back with the strain. And we did some, these studies were carried out in Japan, and we did actually investigations on the fraction and the orientation of the omega and alpha phases, especially we did 5 and 6, and also after aging. And well, for 5 and 6, then we know, for example, the fraction after 5 gigapascals is something like 50-50. But then if we do it at 6 gigapascals, then the fraction of omega phase is actually 70-30 roughly. And then when we age it, it's clear that the alpha phase recrystallizes, statically recrystallizes from in the microstructure, and then we have a lower fraction of the omega phase. So this is an interesting way to control the mechanical properties of the pure titanium, commercial purity titanium alloys, and it's difficult to do EBSD at such fine grain sizes because the grain size is quite small. So the noise or resolution of the EBSD at the same level is not the best. So looking at this kind of omega and alpha crystal structures at higher magnifications using advanced crystallographic techniques, or TEM, for example, crystallography in TEM could give us more information about this phenomenon. Okay, so moving a little bit further into alloys, and I said we did some work on beta titanium. One of our most important results revolve around the titanium 25% atomic percent niobium, that's 40% in weight, synthesized by the elemental powders. So usually, as I said, the stress shielding effect means that if we put an implant of the high Young's modulus material like steel, cobalt, or even alpha titanium, then we will get an effect where we absorb the load only in the implant, and the surrounding bone does not get stimulated by the daily loading and unloading that we do when we move and walk. So eventually, people who are implanted with this kind of devices may get tissue necrosis around the implant, and the implant will loosen, and then this will require to be surgically removed and then reinstalled again. So if we can find materials that are lower in elasticity, more comparable to the human bone, then we can probably avoid this kind of interventions. So beta titanium alloys are one of the most researched fields. People also are doing porous materials. For example, it's popular to do now 3D printing of titanium alloys with porous structures, so that the implant is not only lower in Young's modulus, but also porous, so that the tissues can grow within the implant, and osseointegration is also improved. But in our work, we only do bulk alloys, and we processed from the elemental powders up to 150 turns, and we got some interesting results, especially for the titanium 25%. As I said, the Young's modulus as low as 40 gigapascals, as measured by nano indentation. And also, we have been doing a little bit of in vitro cellular testing, and that will be shown briefly too. So here on the left, you can see how the microstructure can evolve in terms of the powder or elemental distribution. These are SEM images from the center of the discs. These are EBSD composite maps from the middle of the disc, middle portion of the disc radius, and this is the edge. Again, SEM images from the edge. So this is the initial powder mixtures, and you can see here niobium in yellow and titanium in red. And when we do HPT 10, 50, 150 turns, we can clearly see the elemental mixing. It's very nicely done, even in the center and in the edge, of course. As I said, the strain will depend on the radius. So usually the material at the edge will evolve faster and will have a very small grain size. We did XRD, and we confirmed after 150 turns, the microstructure is fully beta phase because of the characteristic peaks, and we see the gradual disappearing of the alpha titanium peak. Even after 10 turns, we don't see it in this composition or this composition. A little bit still at the 25% and 35%, but then gradually after 150 turns, we are fully beta phase, and this is also a nanocrystalline material with a very small grain size. I will show a little bit, a couple slides, the microstructure of a similar alloy, but the grain size here is something like 30 to 50 nanometers. It's a very small grain size crystalline material. Just as a showing how the cell viability goes, we tested a few of our coarse grain versus ultrafine grain HPT materials. We did some coating even with a peptide that's familiar to titanium surfaces. And we, in terms of the fine grain size, we do see a small improvement, but at least we are statistically equivalent in terms of cell viability. So some research works have shown that the cell viability, the integration of cellular tissue, protein addition, and then cell growth is improved when we use ultrafine-grained materials. We did see a little bit of improvement, but at least they are statistically equivalent. And what we wanted to show here also is that the powder consolidated, we did titanium 25 atomic percent, as I said, and also we tried the niobium zirconium alloy. And they are actually equivalent or better than like conventional high strength titanium alloys for implants and commercial purity titanium as well. So we can also apply functional surfaces, biofunctional coatings to these materials, and it's a kind of a promising application that we are looking into to manufacturing at least small medical devices and prototypes, these kind of materials. We also tried high entropy alloys like titanium-based, titanium, niobium, zirconium, tantalum, hafnium. And, the story is more or less the same, with the merit that these are 5 elements that are hard to mix usually, and the HPT process can mix them. After 50 turns, we have a very nice homogeneous elemental distribution, and also we have very small grains. So here you can see in the TM, the grains actually are very, very small. The sample is truly nanocrystalline. There is some degree of amorphization after 50 turns, but you can see here in the diffraction pattern that we have a truly nanocrystalline material. This is the bright field image. This is the dark field image. We calculated the crystal size or grain size is somewhere about 10 nanometers even after we add 5 elements and we process for 50 turns. And you can see here, the beta phase peak. It's a very wide peak. It's full of dislocations. It's a very defected structure, but at the end of the day, it's a beta phase, and we can actually tailor it with heat treatment, probably. Okay, so that's what we've done, or a summary of what we've done around titanium alloys. More recently, we have been working with bioabsorbable magnesium alloys, and in this case, we're actually looking to have the implant absorb into the bone after the fracture or whatever fixation or repair that we need to do in the healing of the bone. So traditionally, in bioabsorbable materials, we actually have to control the corrosion rate of the metal with respect to the mechanical integrity of the whole assembly, the bone implant assembly. So actually, one of the advantages of having bioabsorbable alloys is that, for example, we don't need to keep a permanent titanium implant, for example, after bone has healed, and this can, of course, help to avoid pain, inflammation, discomfort, but also using magnesium, for example, is very interesting for this purpose. It's a very vital element, and also incorporation of other elements that are similar in nature can improve also the corrosion rate. Actually, the challenge with magnesium is that it degrades fast in human body. So we actually need to reduce the corrosion rate in this material so that we can allow mechanical integrity before or after at least hard callus of the bone is developed in the actual fracture site, right? So if we can get mechanical integrity still after hard callus formation, then the bone can continue healing as the rate of absorption of the implant is continuing, or it's faster. So actually, the work in bioabsorbable magnesium alloys has been in controlling or reducing the corrosion rate. So if we look at the mechanism for bioabsorbability, it is related at some point with the grain size. It's related to the grain size. So once we start usually with galvanic corrosion, but then some protective film is formed, mostly for the formation of magnesium hydroxide and also there is some hydrogen evolution in this reaction. And then, the formation of this film will interact very nicely with bone minerals like calcium ions or phosphate ions present in hydroxyapatite, which is the bone mineral. And then we'll see that gradually, material absorption is controlled by grain boundaries. So usually corrosion after, the passive film has been absorbed, then will proceed as intergranular corrosion. And usually it's associated with the grain size. So reducing the grain size is one option that we wanted to try to improve the corrosion resistance or reduce the corrosion resistance of magnesium alloys. And traditionally, people have used calcium also as an element that has good biocompatibility, but also can decrease the rate of corrosion in magnesium alloys. So we tried, and some people have, of course, used magnesium calcium as a standard alloy for controlling or testing as a potential material for biodegradability. So we did HPT on magnesium calcium alloys. 1 calcium, 1% calcium, and 5% calcium were what we tried firstly and most successfully. And we did a very similar processing as we did for the titanium alloys and characterization. So I'm going to go a little bit faster here. We investigated the microstructure by TEM too. We did EBSD observations and we did the tensile test. We have a capability to do this kind of micro tensile tests in Costa Rica as well. So it's a good way to see the mechanical properties. And also we tested the corrosion in the Hanks reagent, which is the simulated bodily fluid electrolyte. And this electrolyte we tested in an electrochemical cell. We control the temperature with a double boiler. And we have the setup here to carry out linear sweep voltammetry and also electrochemical impedance spectroscopy. And we applied some standard models for the testing and measuring not also the corrosion speed, but also the polarization resistance and some other indicators of corrosion and resistance and degradability. So we process the HPT magnesium calcium alloys. We prepare the surface. We have to usually go fast because oxidation is quick in these materials. We protect the connection with epoxy resin, and we make a connection to the electrolyte, and so that we can expose the bulk ultrafine-grained microstructure to the biodegradation. So usually magnesium calcium will have a magnesium matrix and the second phase particles composed of magnesium to calcium. And then we can see here, we tried first, or we started from an annealed microstructure, and we were given some extruded bars from the Magnesium Research Center in Japan. And then with these extruded bars, we cut some discs, and then we processed by HPT. And you can see here that the grain size seems to be reduced, and the dispersion of the particles carried out, especially 1 calcium. We can see that the particles are well dispersed and finer in size. And this is one of the important aspects that to control is particle size, magnesium to calcium, particle size and dispersion. And you can see it probably here more clearly in backscatter images in SEM. So controlling the particles, that's important. What we did see is that in the case of magnesium calcium, we had some kind of more heterogeneous microstructure where some areas were a little bit coarser in grains than others. So we did find some areas where the grain size, average grain size could be 2 microns, but if we actually go to some points, to some regions, then the grain size can be significantly reduced. As you can see, for example, from the backscatter from the dark field images here, grains can be as small as 200 nanometers or 100 nanometers. And we also saw dispersion of these precipitates, or dispersed particles of magnesium to calcium. So at the deformation that we did, which is 10 turns at 6 gigapascals, this is kind of the microstructure is still heterogeneous. So we are actually looking forward into increasing the pressure, or probably increasing the strain, or using large form factor samples, so that we don't need to increase the strain so much, or the number of turns. And then we can, with a larger sample at sufficient pressure, we can get probably more homogeneous grain size. But nonetheless, we do see deformation strain on the microstructures. And when we see the disperse of the magnesium to calcium, and this is shown by gradual disappearance of the magnesium to calcium peaks by XRD. And we did calculate crystallite size and defects from these materials, and they are, of course, well deformed microstructures. The hardness is shown here. As I said before, in this case, the increase in hardness is not so significant, but of course, with the number of turns and with the amount of calcium, then we will get harder or strengthening because of dispersion and dissolution of this magnesium to calcium particles, and that certainly will increase the strain, especially at the periphery of the discs. We did see that the strength starts increasing as well. Tensile tests we did, and actually, for example, we did get very good behavior, especially magnesium 1 calcium 10 turns. The strength is around 208 megapascals, and ductility is 33%. The way we measure it, it's best to compare between samples, because the samples are relatively small and we don't compensate for machine elongation. So comparatively, we see that this is the best. This is probably not the actual ductility or the actual nominal ductility, but what we do see is that it's improved. And also magnesium 5 calcium, for example, 10 turns, it's reasonably well behaved as well. Fracture surface, mostly ductile, as I showed before. So I will just skip this part. In terms of electrochemical behavior, we actually did see very good results. These are the Tafel curves from the linear sweep voltammetry. And if you get this kind of curve, if you are familiar with corrosion, then the balance between anodic and cathodic reaction will give the actually corrosion voltage, and we can calculate from the specific corrosion voltage the corrosion rate. So we did get the lowest corrosion rate of 0.43 millimeters per year in magnesium 1 calcium 10 turns, and this, as you saw before, is one of the best in terms of mechanical behavior. So very promising. This is one of the lowest values when we looked at the literature. So actually, the grain refinement and the mechanical behavior of this material it's promising for metal implants as is. And of course, we can still add some other alloying elements or try some other configurations, elemental configurations that may be allowed some of the disadvantages, for example, to be improved for potential applications of this kind of biomedical alloys. In terms of impedance, also electrochemical impedance spectroscopy, we calculated especially the polarization resistance, which is the lowest in magnesium 1 calcium 10 turns, which is associated with higher corrosion resistance, and it's consistent with the voltammetry. And in general, if you see this plot, this Nyquist plot, then the size of this loop will give the larger the size, that means the higher the corrosion resistance, measured in terms of the resistance of the film that's between the material and the electrolyte. And the same can be said for the body diagram, and it's a way to measure the corrosion resistance. We check the surface morphology, and we see along the fine grains, the corrosion carrying out, pitting corrosion, and what's called the mud crack patterns. And what we can get from this is that the corrosion degradation proceeds rather homogeneously along grain boundaries. So the smaller the grain size, we see that it's improving the biodegradability behavior. Okay. So how much time do I have left? Maybe 15 minutes?
Technically, only a couple of minutes.
Oh, okay. Sorry.
No
Okay.
problem.
Well, then, yes, that's good. So that's the main point was to look at the biomedical materials, and I will show you some of the work we're doing on energy materials. So in this case, we've been doing some work with metal air batteries. What we said before about magnesium and the corrosion resistance can be applied to some other mechanisms. So for example, in metal air batteries, the idea is to corrode the anode, the metal anode, in this case aluminum, and we put it in front of an air cathode and some important electrolyte or some necessary electrolyte to get the electrical energy from the oxidation of the aluminum. And so you can see that controlling the corrosion rate in this case is also important to produce a high energy density. But theoretically, aluminum air batteries are one of the best in terms of volumetric energy density. But the problem is that self-corrosion and also the parasitic reaction that produce hydrogen inhibits getting the most out of these batteries in terms of electrical discharge. So just to summarize, we tried the standard aluminum magnesium is one of the most important systems, prototype systems for this kind of materials, this kind of batteries. And in collaboration with the University of Costa Rica, we assembled them into some nice battery cell. We produce by high-pressure torsion the aluminum anodes, and these aluminum anodes are placed into a potassium hydroxide gel electrolyte and an air cathode that we buy commercially, and we test this battery prototype in the potentiostat, and we get the corrosion. So we did see improvement with grain refinement, not so much in bulk commercial alloys, but in terms of the adding 3% magnesium was one of the best. In terms of battery discharge and corrosion resistance, when these curves are displaced to the lower potential voltage, that means there is an improvement in corrosion resistance, and corrosion resistance in this case means that battery discharge occurs more steady in time and without many drops. So for example, we see here 3 tests of such aluminum 3% magnesium ultrafine-grained magnesium battery cells with very nice energy density and discharge for up to 70 hours or close to 80 hours. And this is one of the work we've been doing, and we've been actually consolidating powders, increasing the amount of magnesium and the amount of strain. You can see here cross sections of discs. This is the center and this is the edge. And what we see is that we can add more magnesium. We can refine the beta magnesium, aluminum magnesium particles. And then at the edge of the disc, we see fewer of these particles. We can dissolve a high amount of magnesium, 3%, which is kind of the solubility limit. So it's kind of a saturated magnesium aluminum microstructure, and it's probably driving some of the good behavior. It's ultra-fine grained, of course, and you can see here with the SAED pattern, the grains are very small with high angles of misorientation. And we can also see this kind of dispersion of the intermetallic particles, which is kind of the merit of the HPT process. The grain size is about 140 nanometers in aluminum. And we did see very good improvements. So as you can see here, 30 turns of aluminum 5 magnesium or aluminum 50 turns, then we will get the lower voltage, corrosion voltage. We also tested corrosion penetration rate. That means just putting the samples in the electrolyte without and measuring the weight, and see how quickly they degrade. And actually, this kind of 5 magnesium with 30 turns was kind of the best in this case. So unfortunately, the powder consolidated was a little bit less stable, but we we do see that the center is probably one of our biggest challenges because it corrodes a little bit faster, and then that probably makes this kind of discharge curves not so steady as we would like. But so improving the dispersion and the grain refinement in the center in terms of using the HPT process for this kind of batteries is the challenge, but we are working on kind of solving this problem. I think I see one hand up. I don't know if there's a question. Sorry, I just see it. There's a Q&A. Sorry, I see.
Yeah,
Okay,
if you want to take the questions now, we can, or we can do them after you're finished.
Okay, I'll just finish up. There's research in hydrogen storage, as I said. So this is kind of a complex intermetallic phases. We can refine them with HPT and get, for example, higher kinetics in hydrogen absorption. And we are doing some of this work. We did a little bit earlier work with titanium oxide. We can synthesize it, as you see here. And for example, this kind of oxides are interesting for photocatalytic conversion. For example, turning light into energy. And we see that, for example, changing the crystal structure of titanium oxide has been proven to displace the absorption spectrum to the visible light. So that's kind of promising for further like photocatalytic conversion and this kind of materials, for energy conversion, getting electrical energy from the sun, and this sort of investigation. So just to end up, as you saw from our work, probably improving the amount of pressure, the amount of strain without giving so much turns. For example, using a larger press, a larger capacity machine can help. And of course, advanced microscopy investigation to check detail in terms of the phases that we have, the relationship between grain boundaries, and some other defects can probably give us some answers of this behavior of these multifunctional properties that I just talked about. So I want to finish with that. I probably extend a little bit here, but thank you so much for the attention, and I'm glad to answer some questions.
Okay, thank you, Doug. And I saw Sibo had his hand raised first.
Oh, hey, can you hear me?
Yep.
Yeah, thank you for the great talk. So that's a very impressive result. So we are also, this is actually Sibo from ASU, also working together with Force on the twister. So we're also using the twister technology to synthesizing some metal sample. But we actually see a lot of cracks forming in the samples. So have you ever observed the similar programs, or do you have any advice on how to avoid those cracks in the sample?
What's the material that you're doing?
It's iron and iron sulfur mixture.
Well, usually cracks we see in like high entropy materials or like oxides. The magnesium also, sometimes magnesium calcium, especially with higher amount of calcium, it's prone. So sometimes you will get cracking. It's a hard thing to avoid, but probably reducing pressure may help. That's the thing that I've seen, that if material tends to crack, you probably need to reduce pressure, and that's probably more effective than reducing the amount of strain, or probably increasing the temperature if you have a capability to increase the temperature on the die. That probably would help. Maybe the strain rate, the torsion speed. You're probably localizing the strain somewhere, and that's evolving into a crack. So you need to probably reduce the intensity of the strain in some way.
Okay. I have another question. So in your presentation, I do realize you use actually the sample pressure instead of the tonnage load. For example, you use like 5 GPa, 3 GPa. May I ask how you calibrate the sample pressure in your torsion device?
So we have a load cell. Actually, this work of the pure titanium was actually done in Japan. So probably my student will be able to answer how in the facility that she used, how do they control? But we have a load cell in our machine, and the load cell, it's calibrated. We were able to find load cell up to 120 tons. That's and our machine is 200 tons. So what we did is that we made a calibration curve with the load cell, and we see it's pretty linear all the way. In case of our press, it's the load, the oil pressure to the load was very linear. So we were able to drive an equation where we can modify the load with the oil pressure. But I'm not sure if our machine is as sensitive as the one my student used in Japan, and I'm not sure how they control it, but we actually do it in this way. So we use the load cell, and we check if we need to lower the pressure, then we adjust the oil pressure and test with the load cell. So, and it was pretty linear. So, and actually from 120 to 200, we just extrapolated and just kind of believe it's linear, but we actually don't know. We couldn't find a larger, commercially, we couldn't find a larger load cell than 120. I don't know if you have, in your machine, probably you have a load cell incorporated, and you can set the pressure.
Okay. Yeah. I will check it out. So those are commercially available, right?
Yes. We actually bought it from, if I'm not mistaken, from Taiwan, the load cell, 120 ton. So you have a 500 ton, so it's kind of a big machine. So I don't know.
Okay, I got it. Thank you.
And then Dan, did you want to ask your question out loud?
Dan, I gave you the permission for the speak, so maybe you can unmute and talk.
Yes. Can you hear me?
Yes.
Yep.
I see your question.
Yeah,
yes,
I posted the Q&A. Yes.
Yes. So no, sorry. The annealing was the initial state. 800 degrees C annealing was the initial state. Then we process at room temperature.
Okay.
And then we age it.
Anneal before you rotate.
Yes, before. Statically.
And then you did it in separate furnace, not
separate
in
furnace.
the torsion device.
Yes. No, we don't have a capability to heat in situ.
Yeah. I just want to make sure. Thank you so much.
Sure.
Okay, do we have any other questions?
I also have one question regarding the Dan's question. So initially you do the annealing at 800 degrees C at ambient pressure, 1 atom pressure. But do you need to make the pellet or something to reduce the porosity, or maybe how you guys like anneal the sample?
In the case that we did, we just did in air. Yes, yeah, we usually grind surface after we anneal. If it's annealed before, and then we just grind it. Yeah, we don't have a controlled atmosphere furnace, but I think my student actually in the pure titanium work, she actually did use a atmosphere controlled furnace, but we don't have that in here. So what we do, we just do it in air. Yes.
Okay, any other questions? If not, let's thank Dr. Sesín again for coming and speaking to us. It's a really interesting talk. I'm a geologist, so I don't really think about metals in this way, and it's cool to see how many of the same ideas apply and how much I could understand, even though I'm not a material scientist.
Good. Actually, the very beginnings of high pressure research by Bridgman in the 1930s, he was doing at Harvard geology research. Actually, he promoted this kind of work as simulating rock under pressure, tectonic plates, and it's kind of a similar field that he actually tested many materials, including this kind of minerals, and that was kind of a way to simulate the effect of like earthquakes or geological formations with pressure at deeper layers of the crust. So that was an interesting thing, that it's driven a little bit from there into materials science.
Yeah, I guess that was really cool. Just thinking about how you can use the degradation of a material to your advantage in some of these applications.
Yes, especially this kind of a battery, and it's good because we don't need a large workpiece for battery, so we can increase the size with some other methods, like doing on a linear way on a sheet of metal and do it continuously, and then just kind of getting the anodes later. So it probably makes sense if the behavior is actually very good.
Yeah.
But we cannot put enough strain, so we need to put enough sufficient strain. So that's kind of the challenge.
All right, thank you again. Really appreciate you coming and speaking with us.